Yesterday we discussed point defect. Again I am recapitalizing that point defect. Point defect, the deviation exists from the ideal arrangement of constant particles around a particular point. It is called a point defect. The crystal is a defective crystal. And this point defect is classified into three types: stoichiometric defect, non-stoichiometric defect, and impurity defect. Stoichiometric defect, again, four types are there. Number one is vacancy defect. Stoichiometric defect means the defect will not disturb the stoichiometry of the compound. Number one is vacancy defect. Some of the lattice sites are vacant due to the absorption of heat from the surroundings. Example, see, this is the arrangement of constant particles. In that, here and there vacancies are there. This defect we call it as vacancy defect. The other name is thermodynamic defect. And because of the defect, there is a decrease in the density of the crystal. Example, non-ionic solids are coming under this category. Second type is interstitial defect. The constant particles are in the interstitial site. See, here I have shown the picture. These are all constant particles. Regular arrangement is there. In that, in between, in the interstices. Interstices, you know very well what is interstice. The gap, the void between the spheres, that is interstices. In that, interstices, some constant particles are present. That defect we call it as interstitial defect. Example, non-ionic solids. And the third one is Schottky defect. Schottky defect means equal number of cations and anions are missing from their lattice site, and electrical neutrality is maintained. Equal number of cations and anions are missing, and this defect you can see in the case of ionic solids. If both cations and anions equal number missing, it is Schottky defect. And because of the Schottky defect, density of the crystal decreases. And where you can see this type of Schottky defect, it is shown by the compounds with a high coordination number and small difference in size of cation and anion. I hope you understood these three types of defects. Example for Schottky defect: sodium chloride, potassium chloride, silver bromide, cesium chloride, and potassium bromide. Next is Frankel defect. What is Frankel defect? One ion is missing from its lattice site and it occupies the interstitial site. It is also called dislocation defect. It is also called vacancy defect and also called interstitial defect. And normally the cations are missing from their lattice site because they are smaller in size and occupies the interstitial site. And the smaller ion is dislocated from its normal site to an interstitial site. Is there any change in the density of the crystal? No change in the density of the crystal. And compounds having the low coordination number and large difference in size of cations and anions shows this type of Frankel defect. Now the pictures I have drawn for Schottky and Frankel. First you take Schottky defect. Cation is there, A plus is a cation and B minus is an anion. And there, say some ions are missing. You see here A plus is missing and here B minus is missing. So A plus and B minus missing from its site. An equal number of A plus and B minus. Here I shown one A plus is missing and one B minus is missing. As a whole, the electrical neutrality of this crystal is maintained, and because of that density decreases. And here you take in Frankel defect, A plus B minus, A plus B minus, this arrangement is there. In that A plus is missing from its site and it occupies the interstices. And this defect we call it as dislocation defect, Frankel defect. And because of the presence of this Schottky and Frankel defect, the conductivity of the crystal decreases and even stability also decreases. Now coming to the non-stoichiometric defect. Non-stoichiometric defect means the stoichiometry of the compound is disturbed. That we call it as non-stoichiometric defect. Non-stoichiometric compound means the number of cations and anions are not same as indicated in their chemical formulae of a compound. That defect we call it as non-stoichiometric defect. Now you take two types of non-stoichiometric defects are there. One is metal excess defect, another is metal deficient defect. Metal excess, when the metal will be excess. Number one is by the anionic vacancies. Number 2 is presence of extra cation in the interstices. So when the metal will be excess because of the anionic vacancies or the presence of extra cation in the interstices. Number 1, by anionic vacancies. The negative ions are missing from its lattice site and leaving a hole and which is occupied by the electron. That means the electrons are trapped in the anionic vacancies. Here the picture I have shown one sodium, suppose you take sodium chloride, Na plus Cl minus, Na plus Cl minus, this arrangement will be there. And when NaCl, same NaCl is heated with the sodium vapor, what will happen? Cl minus from its lattice site diffuse to the crystal and reaches the surface. There it combines with Na plus from Na. Surface Na is there and in here NaCl is there. Now the Na ionizes and releases electrons and Na plus is formed. That Na plus combines with Cl minus and forming NaCl, and now the electrons again diffuse back to the crystal and occupies the anionic site. So electrons are trapped in the anionic vacancies. That defect we call it as metal excess defect. So here in the crystal, number of Na plus is more than Cl minus. As a whole, electrical neutrality is maintained, but more cation is there. That's why it is called a metal excess defect. Now these electrons absorbs the energy from the white light and giving yellow color to that crystal. So whenever you heat NaCl with Na, you get yellow color. Same manner, lithium chloride heated with lithium, you get pink color. And potassium chloride heated with potassium, you get violet color. You can remember easily KCl, K means V, KV, KV, you can remember potassium, KV, KCl with K, you get violet color. And lithium chloride, LiCl, heated with lithium, you get pink color. You can remember LiP, LiP. Lithium gives pink color and KCl with K gives violet color, and sodium chloride plus sodium gives yellow color. Now coming to the second category, metal excess due to the presence of extra cation in the interstices. Whenever you heat the zinc oxide crystal is white in color. Whenever it is heated, it gives Zn2 plus half O2 plus 2 electron and it turns to yellow color. Very, very important board question. Zinc oxide is white in cold and yellow in hot. The reason is because the excess zinc 2 plus get trapped into the interstitial site and electron occupies the neighboring interstitial site. I have shown here your suppose A plus here I have taken, or you can write it Zn2 plus O2 minus like that. In this crystal, this A plus, that is cation, is occupying the interstitial site and electron also occupying the interstitial site simultaneously. As a whole, the electrical neutrality is maintained, but number of Zn2 plus is more than that of O2 minus. That's why it is coming under which category? Metal excess. The second type is metal deficiency. When the metal becomes deficient, and here we have written by anionic vacancy, and here you can write it cationic vacancies. And the second category, extra cation, here extra anion in interstices, that is not possible because anion is larger than cation in size. So only one possibility here, by cationic vacancies, metal deficiency due to cationic vacancies. Due to the missing of cation from the lattice site and presence of cation having higher charge, it is called metal deficient. One example I will give you, you will understand this. In iron oxide, Fe2 plus is there, O2 minus is there, but in the crystal, 3 Fe2 plus are replaced by 2 Fe3 plus. That means Fe2 plus is converted into Fe3 plus and 3 Fe2 plus is replaced by 2 Fe3 plus for maintaining the electrical neutrality. So here which is excess, anion is excess, actually cation is what? Deficient. Here I have given here A plus is missing, but A plus is replaced by A2 plus. So 2 A plus are replaced by 1 A2 plus. So here metal deficient. One place, cationic place is vacant. That's why it is called metal deficient. The last one is impurity defect. Whenever you add impurity to that, you get this type of defect, that is impurity defect. When foreign atoms are present at the lattice site, in place of host atom. Example, whenever strontium chloride is mixed with sodium chloride. Sodium chloride, already the arrangement is there, Na plus Cl minus, Na plus Cl minus, but little SrCl2 is added and 2Na plus is replaced by 1 Sr2 plus. Another example, cadmium chloride is added to NaCl. Cadmium chloride is impurity and or AgCl. You can take even AgCl also. CdCl2 is added to AgCl. Electrical properties of solids. Electrical properties of solids. Based on the electrical properties of solids, they are classified into three types. You know very well: conductors, insulators, and semiconductors. What are conductors? Conductors means the solids which with the conductivities ranging from 10 to the power 4 to 10 to the power 7 per ohm per meter are called conductors. And metals having conductivities in the order of 10 to the power 7 per ohm per meter are good conductors. Insulators means these are the solids with very low conductivities ranging from 10 to the power minus 20 to 10 to the power minus 10 per ohm per meter. And semiconductors means these are the solids with the conductivities in the intermediate range from 10 to the power minus 6 to 10 to the power 4 per ohm per meter. So based on the conductivity of the solids, they are classified into three types: conductors, insulators, and semiconductors. Now we will see the conduction of electricity in the metals. You know very well metals are good conductors of electricity, and they are the good conductors of electricity in the solid state as well as in the molten state. The conductivity of the metals depending upon the number of valence electrons available per atom, and the atomic orbitals of metal atoms forming molecular orbitals. Already we discussed MO theory. Atomic orbitals of metal atoms form a molecular orbital which are so close in energy to each other and they form a band-like appearance. So atomic orbitals overlap and forming a molecular orbital, and these atomic or molecular orbitals, they are arranged in a closed manner and look like a band. If this band is partially filled or it overlaps with a higher energy unoccupied conduction band, then the electrons can flow easily under an applied electric field and the metal shows conductivity. And what is conduction band and what is valence band? You might have studied in physics. The valence band and the conduction band, you take a conduction band means the higher energy valence orbital forming conduction band, and the lower energy valence orbitals form a valence band. That means conduction band means the unoccupied higher energy band is called conduction band, and the lowest energy occupied band is called valence band. And if the gap between the filled valence band and the next higher unoccupied conduction band is very large, the electrons cannot jump to it, and such a substance has very small conductivity and it behaves as an insulator. So conductor means electrons quickly jumps from the filled valence band to the unoccupied conduction band. If the gap is very small, then the electron can easily jump and they are good conductors. If the gap between the filled valence band and unoccupied conduction band is very large, then the electrons cannot jump, then they are insulators. If it is intermediate, then they are called semiconductors. And here the picture shows, you see the first picture shows the metals. In the metal, two bands are there. One is a valence band, another is conduction band. The top one is a conduction band and bottom portion is a valence band. And the valence band may be partially filled or fully filled. Partially filled, the electron jumps from partially filled orbital to empty band. Or sometimes overlapping of atomic orbital occurs, and because of overlapping, electron jumps from filled band to the empty band. These are all called conductors. Example, metals. In the case of insulator, the gap between the filled band and empty band is very, very large, and they cannot conduct the electricity. Electron cannot jump from this band to this band. You take semiconductor, it is intermediate. The energy gap between the filled band and the empty band. This is conduction band, this is valence band. This is conduction and this is valence. And the energy gap is intermediate between these metals and the insulators. It is called semiconductor. Electrical properties of solids. I told already, based on the electrical properties of solids, solids are classified into three types: insulators, semiconductors, and conductors. And band theory of metals I have shown here. In the case of metal, atomic orbitals of metal atoms are so close in energy that they overlap to form a large number of molecular orbitals very close in energy, and this set of molecular orbitals is called band. For example, you take lithium, the electronic configuration is 2s1, I have shown here, and the electrons are there in 2s orbital. This is one lithium atom, this is another lithium atom, like this. You take lithium metal, it is made up of many lithium atoms. Now, in the case of lithium, the lower half of the molecular orbitals are completely filled, because 2s1, this is completely filled, while the upper half is empty. This is empty. On applying electric current, electrons can move into the vacant levels. Hence, the electric current can flow. So, I hope you understood this lithium. And these Li, 2s1, each Li has an electron in 2s orbital. These overlap and forming a molecular orbital. In that, half will be filled and half will be empty. So, filled orbital, lower half orbital. This is empty upper half orbital. And this is called, which band I told? This is conduction band and this is valence band. Now you take beryllium. Beryllium, the electronic configuration is 2s2, 2p0 and 2s2 fully filled. Now the band formed from 2s orbital will be completely filled, hence no conduction of electricity occurs. It is fully filled because 2s2 fully filled. Now actually beryllium is a good conductor of electricity because 2s orbital will overlap now with the empty 2p orbital and overlapping occurs. So overlapping of 2s orbital as well as overlapping of 2p orbital also occurs. Because of that, two bands are formed. One is fully filled valence band, another is empty conduction band. And now the electron can easily move. Now why electron moves? Because of the overlapping of 2s and 2p orbital. I hope you understood this conduction band and valence band. So what is valence band? The lower energy valence orbitals form the valence band. And the conduction band means higher energy valence orbitals form. So the unoccupied higher energy band is called conduction band. The conductivity of these intrinsic semiconductors is too low to be of practical use. Their conductivity is increased by adding an appropriate amount of suitable impurity. This process is called doping. Doping means addition of impurity for improving the conductivity of the metal is called doping. And doping can be done with an impurity which is electron rich or electron deficient as compared to the intrinsic semiconductor silicon or germanium. Suppose you want to improve the conductivity of silicon or germanium, you can add the impurity. That impurity may be electron rich or electron deficient. Finally, the conductivity of the silicon and germanium is improved, and this process we call it as doping. Such impurities introduce electronic defects in them. Now electron rich impurities, suppose you add, what will happen? Silicon and germanium belonging to group 14 of the periodic table, and it belongs to, you know very well, silicon and germanium is carbon family, and they have 4 electrons each in their outer shell. Valence electron means outer shell, they have 4 electrons. In their crystals, each atom forms 4 covalent bonds with its neighbors. And when doped with a group 15 element like phosphorus or arsenic, which contains 5 valence electrons, they occupy some of the lattice sites in silicon or germanium, and 4 out of 5 electrons are used in the formation of 4 covalent bonds with the 4 neighboring silicon atom, and a 5th electron of phosphorus or arsenic is extra and it is delocalized, and these delocalized electrons increase the conductivity of the doped silicon or germanium. And here the increase in conductivity is due to the negatively charged electron. Hence the silicon doped with electron rich impurity is called N-type semiconductor. Now suppose you add electron deficit impurity, electron deficient impurity like group 13, boron, aluminum or gallium, which contains only 3 valence electrons. The place where the 4th valence electron is missing is called electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but in doing so, it would leave an electron hole at its original site. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of electron that filled it. Under the influence of electric field, the electrons would move towards the positively charged plate through electronic holes, but it would appear as if the electron holes are positively charged and are moving towards the negatively charged plate. This type of semiconductors are called P-type semiconductor. The previous one is an N-type semiconductor and this is P-type semiconductor. Here pictures are given clearly, you will understand better. You take silicon or germanium, it is a perfect crystal. Each round is nothing but silicon. This is one silicon, 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 everywhere silicon. And one silicon is in contact with how many other silicons? You see 4. Right, all the sides, 4. Suppose you take this silicon, this side silicon, 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 silicon. And 4 covalent bonds are formed. And now you take, suppose you add an impurity, arsenic, which is a pentavalent. 5 electrons it has, but only 4 are utilized. One silicon is now replaced by as doping, adding arsenic as an impurity. Now 1 electron is excess. When you apply electric field, these electrons move towards the oppositely charged plate, that is positive plate. This type of semiconductor we call it as N-type semiconductor. So here the electrons are moving. So negatively charged electrons are moving. That's why it's called N-type semiconductor. Now you take P-type semiconductor. Silicon is there. Now it is doped with boron. Boron has only 3 electrons. So 4th place is vacant now. This hole we call it as electron hole or electron vacancy. And now the electrons from the neighboring will occupy this hole. And again here hole will be created. Again the electron. In that manner, holes are moving in one direction and electrons are moving in this direction. Suppose electrons are coming here and here hole will be formed. Already hole is here. Now hole is moving this side and electrons coming here. This manner, electrons are moving one side and electron holes are moving in other side. This type of conduction we call it as P-type semiconduction. Now applications of this N-type and P-type semiconductor, where you can use this semiconductors. Diode is a combination of N-type and P-type semiconductor. You might have studied in physics. It is used as a rectifier. And transistors are made by sandwiching a layer of one type of semiconductor between the 2 layers of the other type of semiconductor. NPN and PNP type of transistors are used to detect or amplify the radio or audio signals. The solar cell is an efficient photodiode used for converting the solar light energy into electrical energy. These are the applications of semiconductor. Germanium and silicon are group 14 elements and therefore they have a characteristic valence of 4 electrons and form 4 bonds as in diamond. A large variety of solid materials have been prepared by the combination of group 13 and 15 elements or 12 and 16 to stimulate the average valency of 4 as in germanium or silicon. Group 13 elements and combination with the group 15 elements, you get one compound, right? And group 13, they have 3 electrons in its valence shell, and group 15, they have 5 electrons in its valence shell, and the average valency will be finally 4. So when you combine group 13 elements with the group 15 elements and forming a compound, that compound will have the conductivity like silicon or germanium. Same manner, group 12 and 16 combination. Suppose you take zinc belongs to group 12 and sulfur belongs to group 16. When you combine this, you get zinc sulfide. And zinc, the valence electrons 2 and sulfur, the valence electrons are 6. Finally, the average will be 2 plus 6 by 2 gives you 4. And transition metal oxides including vanadium also have high electrical properties. These are the applications of this solids in conduction. Next, coming to magnetic properties. Magnetic properties means, the solids have a magnetic character. The magnetic properties of different materials are studied in terms of magnetic moments, which arises due to the orbital motion and spin motion of electrons. So every substance has some magnetic properties associated with it. The origin of these properties lies in the electrons. Each electron in an atom behaves like a tiny magnet. Its magnetic moment originates from the two types of motions. One is its orbital motion around the nucleus, and second one is its spin motion around its own axis. So electron, being a charged particle and undergoing this type of motions, can be considered as a small loop of current which possesses a magnetic moment. Thus, each electron has a permanent spin and an orbital magnetic moment associated with it. Magnitude of this magnetic moment is very, very small and is measured in the unit called Bohr magneton. Bohr magneton, BM, and it is the equivalent to 9.27 into 10 to the power minus 24 a meter power 2. On the basis of their magnetic properties, substances can be classified into 5 categories. One is paramagnetic, another is diamagnetic, third one is ferromagnetic, fourth one is antiferromagnetic, fifth one is perimagnetic. There are of 5 types. Now paramagnetic. Paramagnetic substances are weakly attracted by a magnetic field. They are magnetized in a magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. Paramagnetism, already we discussed in bond order prediction, O2. O2 is paramagnetic. When you draw a molecular orbital diagram, you will understand they have 2 unpaired electrons in the antibonding 2p orbital. So paramagnetism is due to the presence of one or more unpaired electrons which are attracted by magnetic field. And examples are given: O2, Cu2+, Fe3+, Cr3+. Next is diamagnetic. Diamagnetic substances are weakly repelled by magnetic field. Example: water, NaCl and benzene are some examples of such substances. They are weakly magnetized in a magnetic field in the opposite direction. And diamagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of electrons cancels the magnetic moments and they lose their magnetic character in the absence of magnetic field. Next is ferromagnetism. Ferromagnetism, a few substances like iron, cobalt, nickel, gadolinium and CrO2, they are strongly attracted by the magnetic field. Such substances are called ferromagnetic substances, and these substances can be permanently magnetized. In the solid state, the metal ions of the ferromagnetic substances are grouped together into the small regions called domains. And each domain acts as a tiny magnet, and in an unmagnetized piece of ferromagnetic substance, the domains are randomly oriented and their magnetic moments gets cancelled. But when the substances are placed in the magnetic field, all the domains get oriented in the direction of the magnetic field and a strong magnetic effect is produced. And this ordering of domains persists even when the magnetic field is removed. And the ferromagnetic substances become a permanent magnet. Once it is magnetized, it never loses its magnetic character. And this domains persist even when the external magnetic field is removed. So they remain permanently magnetized. And ferromagnetic substances, materials, they are used in magnetic tapes in audio recording. Next is antiferromagnetic substances. The substances which are expected to possess paramagnetism or ferromagnetism on the basis of magnetic moments of the domains, but actually they possess zero magnetic moment are called antiferromagnetic substances. Example, MnO. Antiferromagnetism is due to the presence of equal number of domains in the opposite direction. Next is ferrimagnetic substances. The substances which are expected to possess large magnetism on the basis of magnetic moments of the domains but actually have small net magnetic moment are called ferrimagnetic substances. Example, magnetite Fe3O4 and ferrites M2 plus Fe2O4, or in that M2 plus maybe zinc, maybe copper, or maybe magnesium. So the other examples are MgFe2O4, ZnFe2O4. These substances also lose ferrimagnetism on heating and becomes paramagnetic. And here ferrimagnetism arises due to the unequal number of domains in the opposite direction, resulting in some net magnetic moment. And here the picture given, you can understand what is a paramagnetic substance. Paramagnetic means they are weakly attracted by the magnetic field. And ferromagnetic, the domains are oriented in the same direction. And antiferromagnetic means they have equal and magnetic moments but in both the directions. So finally the net magnetic moment is 0. And the ferrimagnetic substances, here you see the net magnetic moment is not 0. The domains have a small net magnetic moment, unequal number of domains in opposite direction.